Okay. Good evening, everybody. Yes. So, any doubts in what we have discussed so far in chemical bonding? Any doubts until this point? Clear? Okay, we shall move on. We are going to learn one of the important theories in chemical bonding, which explains primarily the shapes of and geometry of molecules. All right, it's called VSEPR theory, which is valence shell electron pair repulsion theory. How many of you are already aware of this and you know, you understand? Okay, we'll go ahead. This is one of the important theories. Okay. So we had learned about, Lewis dot structures, correct? So where we had learned, but that it doesn't talk about shapes of molecules, right? So here we are going to learn a procedure to predict the shapes of covalent molecules. Some history about VSEPR. So what is it based on? It is based on repulsive interactions of electron pairs in the valence shell of atoms. As you understand, electrons are negatively charged species. Among themselves, they are going to repel each other, isn't it? How do they accommodate themselves inside one orbital? How many electrons can be accommodated in one orbital? 2 electrons. Although they are negatively charged species and usually they repel each other, how do they still get accommodated within the same orbital? Yes, because of the difference in their orbital spin. Although electrostatic nature is that they repel each other, because of the magnetism that they produce. One of the electrons spins in the anti-clockwise direction, the other electron spins in the clockwise direction, producing magnetic moments in opposite direction. In simple words, you can understand like one behaves like a north pole, another behaves like a south pole, because of which there is some attraction between those electrons. Is that clear? So that keeps them in place inside one orbital. Okay. Some postulates we are going to list them down at one go at this point, but then we are going to see each one of them in detail. Okay, shortly. So, what are some of the postulates of VSEPR theory? If you see, the shape of the molecule depends on the number of valence shell electron pairs. So, when I talk about shape of a molecule, when I'm talking about shape of a molecule, it depends on what? The number of valence shell electron pairs. They could be either bonded electron pairs or they could be what? Lone pair of electrons. What do you mean by lone pair of electrons? Excellent answer, right, Amok? So these are pair of electrons which are present in the valence shell of the atom but are not involved in bonding process. Is that clear? Such electrons are called lone pair of electrons. Very good. So the shape of the molecule is predicted exclusively based on the valence electron pairs. How many lone pairs are there? How many bond pairs are there? Will give us a good indication of what will be the shape of the molecule. We are going to see that shortly. We know that pairs of electrons inside in the valence shell repel one another since their electron clouds are negatively charged, correct? So there will be repulsion between a lone pair. Suppose if an atom has 2 lone pairs, 2 pairs of electrons, those 2 lone pairs will repel among themselves, right? So both are negatively charged species, correct? We call electron cloud. Why do we call electron cloud? Because it has wave nature as well, right? Which means you cannot specifically predict the location of that particular electron. So you say in this region the electron is there, correct? So you call it as electron cloud, all right? So if there are 2 lone pairs present, then those 2 lone pairs will repel among each other. If there are two bond pairs present, what do you mean by bond pair? So let's say water is there, water molecule, H2O. Between O and H, there is one bond. Between O and another H, there is one more bond. So these two are called what? Bond pair of electrons. Is that clear? So will there be repulsion between the two bonds? Yes. Two bonded pair of electrons? Yes. Now you know oxygen, right? Oxygen, what is its valency? Well, in the sense, how many valence electrons are there? Tell me that. 6 electrons are there. Out of which, how many are involved in the bonding process with hydrogen? How many electrons are involved out of the 6 electrons? How many electrons are involved in the bonding process with hydrogen? Out of 6. 2, isn't it? Hydrogen and oxygen are forming what bond? Covalent bond. Hydrogen has how many electrons? Only 1. It brings that to the table. Oxygen gives its 1 electron. So they form a bond. And hydrogen, oxygen, 1 more bond. So how many electrons are used up from oxygen for the bonding process? How many electrons? 2 electrons. How many electrons are remaining in the valence shell? 4, very good. 6 electrons were there. 2 electrons are involved in bonding. 4 electrons are there in valence shell, but they are not involved in bonding. So these electrons they exist as 2 lone pairs. Exist as what? 2 lone pairs. That's why oxygen has how many lone pairs? 2 lone pairs. Water molecule has 2 lone pairs. 2 lone pairs of electrons. 4 electrons which are there with oxygen are not involved in bonding. Those electrons are called as lone pair of electrons. How many lone pairs are there? 2. Why? Totally there are 4 electrons. Each pair represents 2 electrons. Clear so far? So these 2 lone pairs are going to repel each other. The 2 bond pairs are going to repel each other. And also the lone pair and the bond pair are going to repel each other. We are going to see that in detail, right? This repulsion is going to be the basis of the shape of the molecule. Okay, we'll see that in detail by end of today's session. You must be thorough with, I just give you the configuration. I won't even tell you the molecule, but you must be able to tell me the structure. Is it clear? That's very much possible. Okay, so do you understand the statement, guys? Pairs of electrons in the valence shell repel one another, and since their electronic clouds are negatively charged. Next point. The valence shell is taken as the sphere with electron pairs localizing on the spherical surface at maximum distance from one another to minimize the repulsion. So, third postulate is, okay, if there is repulsion, what will happen? If there is repulsion, what will happen? They'll try to be closer to each other or as far as possible from each other. Exactly. That is the third point which you can keep in mind when you're going to draw the structure of the element. Of the molecule. Is that clear? Because of the repulsion, they'll be stable. The molecule will be stable if there is maximum distance between the electron pairs. These pair of electrons tend to occupy such positions in space so that there is minimum repulsion and thus there is maximum separation between them and leading to minimum energy and more stability. Okay. Again, reiteration of the same statement because you have the entire space with you. So it will be a 3-dimensional arrangement. Okay, so we will see that in detail going forward. The repulsive interaction of electron pairs decreases in this order, which I'm going to give you. Lone pair repulsion is maximum. The repulsion between a lone pair and another lone pair is maximum. The repulsive force between lone pair and bond pair is next. And the least is what? Between bond pair and bond pair. One simple explanation why lone pair shows more repulsion is because lone pair only belongs to one of the participating atoms. Whereas your bonded pair of electrons is belonging to what? Both the participating atoms. Therefore, they are kind of stabilized because of both the nuclei. They have attractive force from both the nuclei. So why lone pairs repel more? Because lone pairs are localized on the central atom, whereas your bonded pair is shared between what? 2 atoms. 2 nuclei are influencing, not necessarily 2. Sometimes you have a polyatomic molecule, then many more nuclei are going to impact. those electrons. As a result, the lone pair of electrons in a molecule occupies more space as compared to the bonding pair of electrons. Due to the repulsions between electron pairs, the bond angle reduces. We are getting a little more technical right now. So we will understand this subject as we move on. Okay? Please keep this in mind. There is a point which is mentioned here. What is the point? Between lone pair and lone pair, the repulsion is maximum. Between lone pair and bond pair, repulsion is little less than the repulsion between lone pair and lone pair. Between bond pair and bond pair, repulsion is least. First point. Okay. Next point that you can understand is lone pairs usually occupy more space compared to bond pair of electrons. And because of that, when we have an expected geometry and expected angle, the angles that we will find will be less than those. That's what is mentioned. If there is lone pair of electrons which is present, then the angles between the bonded pair of electrons, right, the bonds, two bonds, will be reduced. We will explain this. It's getting a little more technical, so we'll go in detail as we move along. One example at this point I will quote. For example, methane. CH, right? Now, how many bonds are there? 4 bonds. Is there any presence of lone pair of electrons? No. So it is its geometry is going to be regular geometry. Correct? Whenever there is a presence of lone pair of electrons, we call that the geometry may be distorted. Geometry may be distorted, but still we can predict it. Is it clear? Okay. When we don't have any lone pair of electrons like methane, what is the geometry it takes? We've already seen what kind of geometry it takes. Tetrahedral, right? Tetrahedral, 4 heads, right? So if you can see, any which way you rotate the molecule, it will look symmetric. Is that clear? So it's tetrahedral is going to be the structure of methane molecule. Now let's compare it with, okay, what is a bond angle? What is the angle between 2 bonds, any 2 bonds? It's approximately 109 degree, 28 minutes. All right? Or approximately you can say 109.5 degree. Right? Now, ammonia. Let's take an example of ammonia. Ammonia, if you see, your structure also is dictated by hybridization. sp3 hybridization, we had learned earlier that, the kind of hybridization in methane is what? sp3, correct? 1 s orbital and 3 p orbitals combine, intermix, and give you 4 sp3 equal energy orbitals, correct or not? Right. Now, ammonia, what is the kind of hybridization in ammonia? sp3 once again. Even in ammonia, the kind of hybridization is sp3. And what kind of geometry do you expect? Let's say tetrahedral. But it is not tetrahedral, point number 1. Point number 2, there are only 3 bonds. NH3, right? Unlike CH4. CH4 you had what? 4 bonds. Whereas NH3 you have only 3 bonds. So 3 bonds as in whenever 3 bonds are there, give me an example for a 3 bond molecule. We just looked at BF3, right? Or NF3, okay. What was the angle? What was the structure and what was the angle? We just discussed, right? 120 degree was the angle. It was trigonal, right? Trigonal planar, correct? So ammonia could also, you could expect it to be, because there are 3 bonds, you could expect it to be planar. Or because of the hybridization sp3, you could expect it to be what? Tetrahedral. It's neither of them. Why? Because of the presence of 1 lone pair of electrons. Because you know what is the number of valence electrons in ammonia, nitrogen? 5, right? Out of which how many are participating in bonding? Only 3. It provides 3 electrons to the 1 to each hydrogen atom. So you are having 3 NH bonds. 2 electrons are not participating in bond formation. Those 2 electrons are called what? Lone pair of electrons. And this lone pair of electrons occupy more space. Is that clear? So even if NH3 wanted to be planar, what will happen? The lone pair of electrons will push those, correct? So what will happen is it is almost tetrahedral if you also include one pair of electrons, correct? In CH4 you have 4 bonds, right? 4 bonds form a tetrahedral, right? Tetrahedron. Similarly, your NH3 also, if you include this lone pair also to be similar to one of the bonds, then it will be almost a tetrahedral structure. But then because of this point which we said, lone pair of electrons would like to occupy a little more space. So what they will do? They'll push the other 3 bonds a little closer. So the angle is not 109 degree 28 minutes. So angle between the 2 bonds in ammonia will be what? Less than that, approximately 106.5 degrees. So angle is reduced. Why? Because of the repulsion from the lone pair on the bond pair of electrons. Okay. This you have to get it by today. All right. You to understand, I will try my best to explain it with the diagram. Because if I keep speaking, you have to immediately parallelly visualize. Some of you may not be able to visualize. So that's why we are going to show you the diagrams. You will visualize it, right? And be thorough with it. Okay. It's a very, very simple topic. This is what I was talking to you about. I'll explain in detail for you. So you have methane. Methane has a tetrahedral structure. The angle is, every angle if you see, it's 109.5 degrees. It's a 3-dimensional figure, right? Ammonia, if you see, if you include that lone pair of electrons, then it kind of follows the tetrahedral structure. But then, usually you don't associate lone pair of electrons for deciding the geometry. Geometry is decided only based on the bond pair of electrons. So this angle also you may expect it to be 109.5, but it is not so. It is approximately 107 degrees. Okay. Why is this? Why has the bond angle shrunk? Why has it shrunk? Because this guy occupies more space, lone pair of electrons. He pushes these bonds further. So between the bonds, the angle is less than 109. Clear, students? Let's move on. These structures you need to understand. In the very next class, I will try to bring models and show you. I have, as the teacher, shown you some models to explain you the structures now. I'll bring them so that I will make you explain it, okay? Because I will, today's lecture, if you carefully observe, you will be able to explain the structures too, okay, on next class. Is there anybody knocking the door? Yes, no? Should we try opening? Just check, Roshni. Okay, now we are going to see, we have just discussed overall points, okay? Now we are going to go in depth into every single point which is there, okay? Is your attention at the top? Yes, no? Because you need to be fully involved to get this simple, but it needs your attention. You can't be half present and get it, okay? Will you promise full attention, everybody who is sitting here? Yes? Okay. Fine. So geometry of a molecule, how do we predict? What do you mean by geometry of a molecule? Definite arrangement of the bonded atoms with the central atom in a molecule is known as geometry of the molecule. That's all. So it is only the arrangement of the bonded atoms with the central atom. It doesn't talk about what? Lone pairs. So when we're talking about the geometry, we will not include what? Lone pairs will decide what is going to be the geometry, but then lone pair of electrons will not include to tell the geometry. Is that clear to you? It will impact geometry. Correct? Okay, guys. Now let's move on to, let's look at each one of these postulates in detail. Okay. The shape of the molecule depends on the number of valence electron pairs, lone pair and bond pair around the central atom, right? So we had explained this to you. I'm going to again explain to you with a diagram. Please observe carefully. Okay. So do you get it? Shape of the molecule depends on the number of valence shell electron pairs around the central atom. For example, let's talk about methane. How many pairs of electrons are there, students? Do you understand, students? So we have one bond formed here, one bond formed here, one bond formed here, one bond formed here. There are 4 electron pairs, 8 electrons totally participating, isn't it? So this decides this to have what shape, ma'am? Tetrahedral. Tetrahedral. Now, ammonia, if you see, one lone pair is there. Then there is the 3 bond pairs. Got it? So here also, if you see, right? If you include the lone pair of electrons also to decide the geometry, it looks like a tetrahedron, correct or not? But when you talk about the geometry of any molecule, we will not include the lone pair. So if you don't include the lone pair, then how does it look? Isn't this forming a triangle, guys? So isn't this forming a pyramid? So it's going to be what? Yeah, trigonal pyramidal. All right? Because all those hydrogens are going to form a triangle, correct? And then from the nitrogen and hydrogen, when you join those bonds, it's a pyramid, correct? But what is at the base? Triangle. Therefore, it's trigonal pyramidal. Is that clear, guys? Okay, we'll move on. Any doubts? Okay, next one. Pairs of electrons in the valence shell repel one another since their electronic clouds are negatively charged. This is the second point. I think it's very clear to you, right? Electrons are negatively charged. So because of that, there is repulsion between what pairs? Lone pair, lone pair, lone pair, bond pair, bond pair, bond pair. Is that clear? Okay. Okay. Now, what happens at home? Brothers are fighting, or fighting. What do you do? What is the or let's say in some families, I don't know, maybe children resolve the fights, right? Mom and dad are fighting. Child says, Mom, go to your kitchen. Come on, Dad, go to your bedroom. I don't know. Okay. So what happens, guys? So what do you do? Because of repulsion, there is fight. And what do you do now? If you don't want the fight to happen, what do you do? Keep them in separate rooms. Come on, two brothers are fighting. And what happens? Oh, one pat on your back and go to that room. Brother, you go to that room. Correct? Got it, guys? Yes. Exactly. So position of the electron pair in space around the central atom are such that they are going to minimize the repulsion. Thus, there is going to be maximum distance possible between them. Fourth point. Magnitude of repulsion is such that lone pair repulsion will be greater than lone pair bond pair repulsion. That will be greater than bond pair repulsion. And reason I had told you, bond pair is kind of shared between what? Two atoms. A lone pair is only belonging to the central atom. So the kind of independence, the kind of space that it occupies, the kind of repulsion it provides to the other one is more. Clear? Okay, guys. Now these things are extremely important. If the central atom is linked to similar atoms and surrounded by bond pair of electrons, I repeat, because some part is cut because of the projection. If the central atom is linked to similar atoms, give me an example, quick. Similar atoms, maybe BF3, maybe CH4, right? We're going to see these two examples now. Surrounded by bond pair of electrons. That means, there is no lone pair of electrons, only what you have. Bond pair of electrons. Then the repulsion between them are all similar and the shape will be symmetrical. If there is no lone pair of electrons, are you listening, Amok? If there is no lone pair of electrons, then what will be the kind of bonds? Yes. You have to pay attention. Simple topic, but if you fail to pay attention, you will miss it. Okay. Can you pay attention to every single word? I can do this entire topic in half an hour, all right? I am planning to do it in about 1 hour, 1 hour, 15 minutes, okay? Just because you need to get it, okay? So that doesn't mean, you can browse off. Here or shift your attention. Come on. Simple. Should I raise my voice? Simple, right? See here, similar atoms, similar bonds. BF3 means what? Boron, fluorine, boron, fluorine, boron, fluorine. Same bonds. Same bond length. Same bond angle. Symmetric structure. CH4. All four CH bonds are what? Similar. Why? Because it's between the same set of atoms. Structure will be symmetric. Is that clear? Okay. Repulsion will be similar. Repulsion will be similar. You can keep all that aside. Okay. Fine, guys. So what is this? Let's take example of BF3 molecule. What is, you know, we already discussed this. What is angle, children? What is the structure? Trigonal, planar. BF3. We are talking about BF3. Boron trifluoride, ma. Why are you getting trigonal pyramidal in ammonia? Because of lone pair. Very good answer. Why are you not getting pyramid here? There is no lone pair, ma, so it can accommodate itself in a plane. Clear to you? Yes, good. Observe. So BF3. So the first one we are talking about is what? Boron trifluoride. Example. So what is this? Trigonal planar. What is the angle? We've seen many times. How much? 120 degrees, right? Now next one we are seeing is what? Methane, carbon tetrachloride, whatever you can say, right? So carbon as the central atom, identical atoms are attached to it. All right? So what is the structure, students? Tell me the structure. Tetrahedron. Is that clear? Okay. So let's move on. Next one. If the molecules have different repulsive interactions between the electron pair around the central atom, then the shape will be irregular or distorted. So in the first case, if you see, what is it? It could represent methane or carbon tetrachloride, etc. It's a tetrahedron. What could be this one? Any guess? We just saw ammonia. Yes. So why is it distorted? In the sense, why is it not the regular expected shape? Although it is sp3 hybridization. Because of the lone pair. So what is the structure? Trigonal pyramidal. Whenever there is a lone pair, so there is some kind of distortion which has happened. Why do I say distortion? Because the expected angle is what? 109.5 degrees. It is not so. Correct? Can you predict what this molecule could be? H2O. Excellent. Right? A similar cause, let's say carbon dioxide. Carbon dioxide, if you see, the linear guy, correct or not? H2 also could be linear, right? But why is it not linear? Because of two lone pairs. Right? So this angle is much lesser than, otherwise it will be like, so you have two lone pairs and these two. If you even include the structure of, including the lone pair, it will be tetrahedral. But then, that is going to be, because of lone pairs, that occupies more space. So this angle, at least tell me this answer, okay? This angle is going to be 107, 109 or less than both of them. Less than both of them. So it's going to be around 104. Why is it so? Why do you expect so? Because of lone pairs. There are two lone pairs, not one lone pair, two lone pairs. Excellent students, right? So these two structures, I can call them as what? Distorted. This is what? Symmetrical. Okay? Let's take example methane. Here, let's say ammonia. Because there is a lone pair which is present here. Let's take water. Let's say this angle is 109 degree 0.5, 109.5 degrees. This is 107 around. This is around 104. Because of presence of what? How many lone pairs? Two lone pairs of electrons. All right. Okay, let's ask this question. Please answer this one. Which option? Second option. Methane, there are no lone pairs. Ammonia, one lone pair. Water, two lone pairs. Order of repulsions. Come on, quick. First one, lone pair repulsion is more than lone pair bond pair. That is more than bond pair. Very good. Okay, now we will apply this to find the structures. Okay, very, very important. Fine, this is what is given in your textbook. We are going to discuss them. So, number of electron pairs, right? Molecules having bond pairs only. You see? That means what is not present? Lone pairs are not present. So, very, very simple to predict their structures. If there are two bond pairs, the molecule is going to be linear. If there are three bond pairs, it's going to be diagonal planar. If there are four bond pairs, tetrahedral. Five bond pairs, trigonal bipyramidal. We are going to see that. Okay. Six bond pairs, octahedral, or I can say it's going to be square bipyramidal. Correct or not? We'll discuss that. Okay. Fine, guys. Now let's look at this first. What is this? BeCl2, beryllium dichloride. So what is beryllium dichloride? What is structure? It's a linear molecule. What's the angle between the bonds? 180 degrees. There are two bonds. Maximum repulsion. 180 degrees apart. Clear? Now let's look at this one. So, examples for molecules having two electron pairs. Even you can include what? Yes, tell me. No. Sorry? Okay, no problem. So H2O, what? H2 and all, don't take part here. Why? Because there is presence of lone pair. So here we are talking about only electron pairs. So where there are two electron pairs, then what do you have? You have a structure, you have the formula AB2, right? So like examples are beryllium dichloride, mercuric chloride, beryllium trifluoride, magnesium difluoride, magnesium chloride, etc. All these are what kind of hybridization do they undergo? sp hybridization. sp hybridization leads to a linear structure. There is a connectivity between hybridization and structure. We will review once again hybridization after completing VSEPR. Okay, fine. So now, do you get it, guys? So if there are two lone pairs, not two lone pairs, two bonded pairs, and what happens? They repel maximum, and then 180 degrees apart. If you keep them, molecule will be stable. Correct? Next, let's look at example of BF3. What do you think? How many bond pairs are there? 3 bond pairs are there in the plane. How far must each one of them be? 120 degrees between them, isn't it? So what kind of hybridization can you expect? sp2 hybridization, right? What will be the angle between each of them, each of the two bonds? 120 degree. Examples: BF3, BCl3, aluminium trifluoride, aluminium trichloride, boron trichloride. Correct? All these. Clear, guys? All this must be fingertips. Are you all observing? Yes. Methane. Okay, how many bond pairs? 4 bond pairs. How many lone pairs? 0. Very good. What kind of hybridization? sp3. So 4 bond pairs. Molecular geometry is what? Tetrahedral. 109.5 degrees or 109 degrees, 29 minutes. Methane, CCl4. What is this? Phosphorus pentachloride. Phosphorus pentachloride. Now observe here. What is the geometry now? What is the geometry? Come on, tell me. Trigonal bipyramidal, because you have a triangle here, and on top there is one bond, and bottom one bond is there. If you see, this forms a pyramid. Bottom also you have a pyramid. Therefore, two pyramids are there, bipyramidal. But the base is what? A triangle. Are you able to visualize that, students? Yes. Is a triangle. There's a pyramid at the top. One at the back. Are you able to visualize this? Right? So it's trigonal, bipyramidal. Correct? So the kind of hybridization will be sp3d. sp3d. So how many bond pairs are there? 5. And what is the structure? Trigonal, bipyramidal. Yes. So now tell me, what are going to be the angles? See here. So there is a triangle here. So the angle between those bonds will be what? 120 degrees, like BF3, correct or not? What about the bond angle between this AB and this AB? Aren't they at right angle? So if I say this, the three AB bonds are along the, let's say this is x-axis, this is z-axis. Let's say it is on the xz plane. Then the AB bond which is at the top is what? Along the y-axis, isn't it? Positive y-axis. The AB bond which is there down is along the negative y-axis. So what is the angle between y-axis and xz plane? 90 degrees. So there will be 90 degrees between the vertical and the. So this angle will be 90 degrees. So three angles will be 90 degrees, right? And from the bottom also, if you see, those angles will be 90 degrees. But in the xz plane, the three bonds which are there, what will be the angle between them? 120. What is the angle between the bond which is at the top and bottom? 180 degrees. Because AB is positive y-axis, the other AB is negative y-axis. So angle is 180. So all the three angles are present in this molecule. So this angle is 90 degree. This angle is 120. And the total angle is, the angle between these two is 180. Okay, example is PCl5. sp3d hybridization. Next, SF6. Come on, tell me more. SF6. Octahedral. Very good. Correct? So if you see, this gives you a square here and then a pyramid. Correct? And there is one more down. Or in other words, this is a symmetric structure. Octahedral, 8 heads. Each one of them can be considered as a head. Alright? So what will happen? If you rotate it in any direction, the molecule will look identical. What is the kind of hybridization now? sp3d2. 5 bonded pairs. How many bonded pairs? 1, 6. I'm sorry. 1, 2, 3, 4, 5, 6. Are you able to visualize this? Octahedral. So what will be the angle between the four of these bonds? 90 degrees. And so top one and anything on any of these? 90. What about the top and bottom? 180. Example, sulfur hexafluoride, SF6. Tellurium hexafluoride, TeF6. Okay, guys, this is a structure. I hope this gives you clarity. Okay, now how to remember this, okay? If you want a technique to remember, okay? So first write this 2, 3, 4, 5, 6, right? 2 bond pairs, 3 bond pairs, 4 bond pairs, 5 bond pairs, 6 bond pairs. The mnemonic is Laddu, not Laddu. Laddu, whatever you can say. Okay, LTT. O. What is L? Linear. What is O? Octahedral. These 3 shapes are going to have T in them. 4 heads. What is 4 heads, guys? Tetrahedral. And 3, triangle, trigonal. planar. And the fifth one is what? Trigonal dipyramidal. This can be used as a mnemonic. All right? Clear? So if I give you the how many bond pairs are there, you must immediately be able to tell the structure. Shall we move on? Any doubts in this? Okay, now that's the next part in your NCERT, which is molecules having bond pairs and also lone pairs. Here you have to watch out for these repulsion concepts and accordingly decide. Okay. So if the molecule is of the type AB to E refers to what? Number of lone pairs. AB2 is what? How many bond pairs? 2 bond pairs. AB2. E is what? 1 lone pair. You can call it as E or L. 1 lone pair. Then AB3. What is AB3, ma'am? How many bonds? AB, 3 bonds. Then 1 lone pair. Then AB2, E2. Then you have AB4E. Okay, we'll see each of them in detail. Okay. By end of this next few minutes, right? You must be able to tell. If I tell you how many bond pairs, how many lone pairs, instantly you must tell me what is the structure. Second point, if I tell you the compound and ask you what is the structure of it, you must be able to tell. Okay, that's the work that we'll do in the next 15-20 minutes. All right? What is the time now? Yeah, sure. Okay. Geometry of some simple molecules or ions with central atom having 1 or more lone pairs of electrons. All right, first, of the type AB to L. AB to L means what? How many bond pairs are there? 2 bond pairs. AB. And 1 L is there. So that means 1 lone pair. Correct? Any example can you think of? 1 lone pair must be there. 2 bond pairs. So what will be the structure, guys? Expected structure. What will it be? Trigonal. Planar will be the expected structure. When I'm writing structure here, it's not the final structure. What is it? Expected structure. Because if this was 1 bond, this was another bond, this was another bond, what will you get? Like BF3, what will you get? Trigonal, planar. But now it is not so. Why? Because this guy is a lone pair, he'll repel these 2 more. The angle between them, can you tell me, will it be, ideally it should be what? Now what do you expect? Less than 120, that's it. Because this guy will push these 2 more. So the structure is called bent. Structure is called bent, that's it. It's bent, that's it. Example, tin and lead. Tin chloride and stannic chloride and lead chloride, 2. Lead 2, right? Valence is 2. You must know the examples. Right, that's very, very important. 1 lone pair will be there and there is 2 bond pairs. Okay. Clear? Can we move on? So lone pair, bond pair repulsion is much more than bond pair repulsion. So the bond angle will be reduced. Okay. One more example is sulfur dioxide. Of course, here there is a double bond. But if I say, this is one, there is a lone pair. 1 lone pair is there. This is again is going to have what structure? Bent. What is the structure? Bent. Now let's move on. Let's look at 2 bond pairs, 2 lone pairs. This I'm sure you know the example. So AB to L2. What is AB to L2? AB, 2 bond pairs are there. And L2 refers to what? 2 lone pairs. In your textbook, E2 is given. That's fine. You can either use E or you can use L. So how many bond pairs are there? 2 bond pairs. How many lone pairs are there? 2 lone pairs, right? How will be the arrangement of the... See, normally AB2 means 2 bonds are there means it should be linear, correct or not? But what is going to happen here? You're going to have lone pair, another lone pair is going to be there. So it is almost like a tetrahedron, correct or not? So the arrangement of these 4 will be what? Tetrahedral. But that's not the shape. Because when I'm talking about the shape of the molecule, I will not include what? Lone pairs. So once again, how does it look, ma? Bent. So what is the structure? bent. That's enough. Is it clear, guys? Examples: water. How many lone pairs are there? How many bond pairs are there? 2. Clear? Any doubts? You have a doubt, we'll not move further. Okay? We'll stop, explain that and move on. Is it clear? Are you attentive? That's more important. If you're attentive, you will get it. It's simple. Reason: lone pair repulsion is much more than lone pair bond pair repulsion. Which is much more than bond pair repulsion? Because the bond angle is still reduced. It's around 104 degrees. Okay? Example: water. 2 bond pairs, 2 lone pairs. Okay? The next one, I don't think we have it in the table, but it's an additional information. So 2, 3. What is 2, 3? 2 bond pairs and 3 lone pairs we are going to have. That clear? So we are going to have 3 lone pairs. This molecule will be linear. Shape of the molecule Xc, F2. Okay, next one is what? 3, 1, 3, 1. What is AB3L? 3 AB bonds. That means 3 bonds, bond pair of electrons, and 1 lone pair of electrons. So I can call it as 3, 1. How is the arrangement going to be, students? Tetrahedral, very good. But that's not the final one. So if you see the overall arrangement, it is what, like tetrahedral? But because lone pair is present and we will not include it, so what is it going to be? Trigonal pyramidal. Example: ammonia. Instantly you must be clear. So tetrahedral is going to be the kind of arrangement. But the structure is going to be what? Trigonal pyramidal. Why trigonal pyramidal? Did we not discuss that? We discussed, right? Nitrogen, hydrogen, hydrogen, hydrogen. The lower part forms a triangle. You see? Lower part forms a triangle. The upper one, NH bonds, forms a pyramid, correct? It's trigonal pyramidal. NH3 is a typical example of your AB3L type. Clear? So due to the repulsions between lone pair and bond pair, the bond angle and between the bond pairs is reduced. So it's not 109 degrees 28 minutes, it's approximately 107 degrees. Okay, guys? So it's 3, 1. So 3 bond pair of electrons and what? 1 lone pair of electrons. Right? Okay, now next. Next, what are we looking at? AB3, L2. 3, 2. So what is it? 3 bond pairs and 2 lone pairs. Very good, very good. Correct. So this is going to be the structure, guys. Alright? 3 bond pairs and 2 lone pairs. So it's a trigonal bipyramidal. So what is going to be the structure? Trigonal, like PCl5. PCl5, correct? So you will have what? Central atom. Three bonds. Then one on top, one in the bottom. So this forms a triangle. These form pyramid. So trigonal pyramidal, but then it is there both sides. So it's trigonal bipyramidal is the structure including the lone pairs, right? But it will end up being what? A T-shaped molecule. It's going to be ending up being a T-shaped molecule. Why is it so? We'll see that. Okay. Example is trifluorochlorine, right? Or chlorine trifluoride. Okay, we are going to see here. Now, can you tell me, students? Can you tell me how many bonds are there? Chlorine has 3 bonds with one each with fluorine. Okay, so you get ClF3. How many valence electrons are there in chlorine? 7, right? And how many are involved in bonding now? 3 are involved. How many are remaining now? 4, right? 4, you can split them into how many pairs? 2 pairs. So these two, there will be 2 lone pairs of electrons. All right? Lone pairs are at equatorial position, so there are less LP-BP repulsion as compared to all other possible structures. We'll understand this equatorial position shortly. Okay. See here, guys. Now, what will happen is, listen here. Observe carefully. Are you able to visualize this? I should choose a different color. Let me just try choosing a different color. I hope students observe. So I hope you can observe. These 3 form a trigonal structure, correct? These 3 form a trigonal structure. What is this, guys? Pyramid on one side. It's going to be another pyramid. Are you getting it? So it is what? Trigonal bipyramidal is the basic thing, PCl5, right? But of course, we don't include the lone pair, right? If you exclude the lone pair, then what does the structure look like? T. So it's a T-shaped molecule. Are you able to understand? So it's a T-shaped molecule. You should not include the lone pairs for getting the shape of the molecule. So, but it is based on trigonal bipyramidal. That you are getting it right. How is the shape obtained? Correct? You must be crystal clear about it. Okay. Clear? Should I explain again? Yes, I can. Once more. Yes, sure. Yes. Now observe cyclic others. See here. Now what is this compound? PCl5, right? So you have all these are identical bonds. So this is your phosphorus, and these are all your chlorine atoms. No lone pair of electrons. Is it clear, students? Phosphorus, pentachloride. Now we are talking about the structure of this. All right. Are you able to visualize this cyclic others? What is that? Triangle, correct? Or you can call it as trigonal, correct? Okay. Now, what is this? Tell me. It's a pyramid. It's a pyramid, isn't it? Right. So it is trigonal, pyramidal so far, correct? What is this? One more pyramid, isn't it? So how many pyramids are there? Two pyramids are there, correct? One pyramid like this, another pyramid like this. Are you able to visualize? In the middle, what do you have? Are you getting it, guys? In the middle, you have a triangle, that's the base. So one pyramid on that side, one pyramid on this side. So it's what? Trigonal, bipyramidal. Trigonal, bipyramidal is the structure. Is that clear to you? Right. Okay. Now, there is no lone pair, no lone pair here. There are only 5 bond pairs: PCl, 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 PCl. 5 bonds between phosphorus and chlorine, identical. Okay. Now let's move on. So I hope you're clear with the structure, right? Now just observe here. In this molecule ClF3, if you see, there are 3 bond pairs between chlorine and fluorine. And how many lone pairs? 2 lone pairs. We already saw chlorine's valence electrons are 7. 3 are utilized for bond formation. How many are left? 4. They can be split into 2 pairs. So do you understand? So if you just look at this position, the lone pairs are occupying here. Are you able to understand? So if you include the lone pairs also, then what kind of a structure will it form? Trigonal bipyramidal. But anyways, we are not considering that shape. When we are talking about shape of a molecule, we don't consider lone pair of electrons, only the bonded pair of electrons, right? What shape is it now? If you leave out those two wings, if you cut off, then what is that? It's just T, isn't it? It's T shape. Do you understand now, Sai Kiran? Is it clear? Okay, great. So are you clear, guys? If you see, this is AB3L2, which means 3 bonds and 2 lone pairs. Let's move on. Let's go to AB4L. Tell me what is AB4L? 4 bond pairs and 1 lone pair. How will the arrangement be? Come on, tell me. Look at this. This is also going to be what? Trigonal bipyramidal, isn't it? So this is going to be triangular. Then you have pyramid on 2 sides. So it's what is the structure? Trigonal bipyramidal, but it's including the lone pair. But because lone pair is not going to be included, what does it look like, guys? Is it not looking like seesaw? That's exactly the structure called. Clear? Examples: SF4, sulfur tetrafluoride. Again, the lone pair is on the equatorial position. See here. What do you mean by equatorial? This is axial. This is equatorial. Equatorial, we just learned in straight lines one of the questions, right? Perpendicular bisector. You remember? Find the equation of the line which bisects perpendicularly the line joining 2 points. Correct or not? So in mathematics, we call something as perpendicular bisector. In physics, we call it as equatorial. In chemistry also, we call it as equatorial, right? So this is your axial line. This plane is called equatorial plane. I will just draw it for you. Come on, tell me, guys, what is this line called? Axial line. What is this plane called? Equatorial plane. It is exactly at the midpoint you draw the plane. Clear? For example, let's say I have the structure, right? Let's say, just hold this. Hold this pen here. Hold one more pen here, okay? So now what is this line, guys? Axial line. What is this plane called? Equatorial plane. When your lone pair of electrons is in the equatorial plane, most stable. That is the reason that will be in the equatorial plane. Clear? Okay, guys. So do you understand SF4 structure? What is there? There is a how many bond pairs? 4 bond pairs. How many lone pairs? 1 lone pair. Actually, what structure, including the lone pairs, if you see? Trigonal, bipyramidal. But now, you don't consider the lone pair for knowing the shape of the molecule. So what is the shape of the molecule? Seesaw. Clear? Next. What are we going to? Come on, tell me, what does it mean? 4 bond pairs, 2 lone pairs. So how will the arrangement be? Octahedral, isn't it? It's like having 6 bonds. If 6 bonds are there, what? 4 of them will be planar, correct? Square bipyramidal, correct or not? So what is this? Octahedral. When I say octahedral, what is this? You have a square here, then you have a pyramid. Bottom also there is a pyramid, correct? But if you leave out this 2 lone pair electrons, once again, these lone pair electrons would be happy to be on the equatorial line. But what is the structure now? It's only on that plane. So square, planar. What is the structure? Square, right? That A, that B and all, if you join, what do you get? Square. It is square, planar. Examples: xenon, tetrafluoride. Usually, rare gases don't combine, but then there are some special compounds which are formed. When we discuss something on group 18 later, we'll be discussing about the compounds formed. Earlier we had seen xenon difluoride also. Yes, XeF2. What was the shape of the molecule? Linear it was. Fine. Now is this okay, guys? ZeF4, what is the structure? Square planar. Do you understand why? Is it clear to you? So it's just a square here. We're getting a square here. Where are our lone pairs? Are you clear? Yes or no? Okay, guys. Next, let's move on to AB5L. Now tell me, how many bond pairs, how many lone pairs? 5 bond pairs and 1 lone pair. What do you expect the structure to be? Yes? Yes? Arrangement of electron pairs will be octahedral, right? Correct? But then what is going to happen? This lone pair of electrons is not considered, right? So what is it going to be? Come on, tell me. What do you have here? Square. What is this forming? Pyramid. So square, pyramidal. Square, pyramidal. Is that clear? Examples. Bromine pentafluoride. PrF5. All right. You can see this structure is clear to you. So you have a square, you have a pyramid being formed. Correct? So it's square pyramid. A lone pair of electrons is on the equatorial line. Any doubts? Okay, so now all these compounds, all these, as is clear, how many of you are clear with this? You must be thorough before we meet for the next class. I just tell you the compound, you should be able to get it. I'll just tell you how many bond pairs, how many lone pairs. I'll give you the structures. Next class when we meet, I'll bring the models. Okay. So I'll ask you to form this. So you should form square, pyramid, or let's say octahedral or tetrahedral, so that your understanding will be accurate. Okay. That will be the assignment next class. Become prepared. Not just theory, but also concept. Come on, answer this one. Which of the following it has octahedral shape? You must remember these things. Okay. SF6. Very good. What is the number of lone pairs and bond pairs in xenon? In xenon tetrafluoride. Yes, 4 bond pairs. Come on, tell me. Which is correct? 4 bond pairs, no doubt about it, correct? How many lone pairs? One on the top and another on the bottom, right? And what is the structure? Square, planar, but actually the original structure is what, including the lone pairs? Octahedral, right? Or square, bipyramidal. Clear, guys? These things must be very clear for you. Okay, merits and demerits. We'll just look at the merits as of now, and then we will. What is the time now? 5:30. We'll just look into one slide, merits, and then conclude. Okay. So merits of VSEPR theory. What is it? I don't have to remember every molecule, yes or no. If I just can understand their valence electrons, how many bonds are formed, correct or not? If you say, let's say SF6, I am telling you. Sulfur, what is the valence, the number of valence electrons? 6. Then what I can understand? F6. 6 only bond pairs are there, correct or not? So 6 bonds have to be accommodated. How will you accommodate it? Then octahedral structure. 4 will be on the plane, square planar. 1 on top, 1 on bottom, right? PCl5. No lone pairs. Understood or not? 5 bond pairs. 3 will form a triangle. 1 top, 1 down. Trigonal bipyramidal, correct or not? So just with a concept, I am able to answer this, right? So it's not necessary to remember the shape of all the molecules, but if you should just know the types. Correct? Only electronic configuration is required, isn't it? You don't require anything more. Electronic configuration or number of valence electrons you require to draw the shape. Total number of valence shell electron pairs in the central atom can predict the geometry of the molecule. Demerits, I'm not sure if I have, yeah, some of them, right? It failed to explain the shapes of certain isoelectronic species. What are isoelectronic species? Species having the same electronic configuration. See, it based on the number of valence electrons. Now, if you see these, both of them have about 56 valence electron, 5. They are predicted to have pentagonal bipyramidal, but that's not the case. However, when you do certain experiments, you understand that these bonds which are supposed to be on the equatorial line are not coplanar. Okay, so we will ponder into this a little later. Okay. VSEPR theory again failed to explain the shapes of transition metals. These compounds, right? They are again supposed to be pentagonal bipyramidal because it has 7 electron pairs. Because if 7 electron pairs are there, how do you arrange them? 5 of them in one plane, pentagon. 1 on top, 1 on one bottom. So pentagonal bipyramidal, understood? And it's not based on quantum, it doesn't take into quantum effects. Okay? When I say quantum effects, you know, right? Wave nature of electron is also to be considered. It does not help in predicting the nature of the molecule, whether a molecule is paramagnetic, diamagnetic, or ferromagnetic. What do you mean by paramagnetic, students? It has some magnetism, positive magnetism. That means if you bring a magnet closer to it, it will feebly be attracted to the magnet. What is ferromagnetic magnetism? What do you mean ferromagnetism? Yes. You bring a magnet closer to it, it will be greatly attracted to the magnet. Example for ferromagnetic materials: ferro, iron, and alloys, right? Nickel. All these are ferromagnetic substances. Examples for paramagnetic substances: aluminium, oxygen, etc. What are paramagnetic? They have non-zero magnetic moments. That means they are feebly attracted. What are diamagnetic substances? They ripple. When you have a diamagnetic substance placed in magnetic field, it's repelled by the magnetic field, which means it has paired electrons. It does not have electrons which are alone in an orbital. Is that clear? Okay, so their magnetic moments are cancelled. So clockwise moment will be cancelled by anti-clockwise moment. Okay. So with this, I think we'll probably take one question and then we'll conclude today's class. On the basis of VSEPR theory, predict the shapes of the following, guys. Can you predict the shapes of the following? SiF4, silicon tetrafluoride. Any guesses? Ammonia, you've removed a hydrogen, has left it as a H plus. There is a minus charge on it. What will be the shape? At least you must tell me C2H12. Acetylene, what is it? Acetylene, what is it? Ethine, what is it? Linear, of course, linear, sp hybridization, correct? What about ammonia? It was pyramidal, right? Now NH2 will be good. SiF4. Yes. So first one is tetrahedral. Second one is a V shape, or you can say pent. Pent is absolutely fine. Cylindrical, or you can call it as linear. All right. Come on, this must be told immediately. Yes. Already answered. Lone pair and lone pair. Any guesses? Come on, I have 7. Iodine. Okay, now you're thinking whether lone pair of electrons are there or not. Iodine, what is it? It's coming in halogen family. What will be the valence electrons? 7. So 7 bonds are formed. So there are no lone pairs. 7 bonds, if you have to accommodate, what should it be? Yes, very good. Pentagonal bipyramidal, because 5 bonds you will accommodate in the same plane as a pentagon. 1 bond at the top, another bond at the bottom. So it will be forming a pyramid. What kind of pyramid? Not square pyramid, not a trigonal pyramid, but what? Pentagonal pyramidal. This option is correct. Come on. SF4. See, lone pairs love to be on which position? Equatorial positions, isn't it? And one lone pair. Why one lone pair? Because you know about SF6, right? So 6 bonds it can form, 6 electrons it has. SF4 means only 4 electrons have been used. So 2 electrons are remaining. That means one lone pair is there. So it forms what? Yeah. So your bond pair will be in which? Sorry, lone pair will be in equatorial plane. Okay, guys. So I think we are done. Right, guys. So with this, we will conclude today's session. And in the next session, we will do models. I'll give a quick kind of test for you guys for about half an hour. Then the next 1 hour, we'll be doing molecular orbital theory and valence bond theory. We'll just touch because already we have learned hybridization and all that. So we'll just quickly revise that. But we'll give more focus on molecular orbital theory in the next class. Okay? All right, students. See you all.